Okay, here's a simple first problem. Sorry it took me so long to get it out to you. Uh, it's kind of an oversimple problem, but that's a good place to start, and there's a couple of instructive points along the way. Um, this problem introduces, in a very simple way, reference frames. The topic is relative motion of two constant velocity bodies. So these two bodies are going to be trains because trains are cool, are not going to change speed at all during the course of this problem. A passenger train traveling at velocity v1, this direction shown by the arrow, follows a freight train with velocity v2 in the same direction, also shown by the arrow, moving down the track. At this instant, the trains are separated by 50 meters, shown here. The first question, under what condition will a collision occur? Condition or conditions if there are multiple requirements. And question 2, if we set v1 equal to 20 meters per second and v2 equal to 15 meters per second, in how long will the trains collide and where? Starting with 1, intuition tells us that, well, any time that the following train is traveling faster than the leading train, we can expect a collision. And intuition is completely correct in this case. Because we're moving in just one restricted dimension, all we can do is move along this line. If the following one is moving at a higher velocity than the leading one, well, eventually the following train will need to move through the leading train at some place down here. That can't happen without a collision. Now, in this case, we're assuming that the two trains have a long way to go, as long as we need to make a collision happen, if it will. And so we can simply say that if v1 is greater than v2, there will be a collision eventually. Anytime v1 exceeds v2, we get a collision. Eventually. And this eventually, the fact that we have eventually to work with, is sort of implied by the fact that we're talking about constant velocity bodies. They can't come to a stop if they're constant velocity bodies. Number 2, we ask this particular question. Well, first, we do have v1 greater than v2, so we expect a collision. Now, there's 2 ways to move forward with this problem. The way that might be natural is to just say, well, okay, I've maybe looked at or thought about or solved problems with one body, so let me just look at one body and consider its location in time. Okay, but then at every time I'm going to have to compare to, okay, at that same time, where is the other body? And then step that along in time forward until I see that this body has moved in front of this body. And then I say, oh, no, that's too far. Back it up now, because it couldn't have passed it. I've gone past the collision, and then you sneak backwards and sneak forward and find your way. And that's a pain. Now, for a problem this simple, you could jump ahead to the solution relatively quickly doing it that way. But The point of the problem is to introduce the idea that by choosing a different frame of reference, we can solve the problem a lot easier. Instead of looking at the velocity of this train relative to the ground, which is v1, and the velocity of this train relative to the ground, which is v2, we can instead ask about a more relevant velocity, which would be the rate of closure between the trains. In this case, they're moving in exactly the same direction, and we have that the trains close the gap at, we have v1 minus v2 equals 20 minus 15 equals 5 meters per second. So, in how long will the trains collide? Well, they're 50 meters apart, and the closure rate is 5 meters per second. And so we have that, well, we know that distance equals velocity times time. If we solve for time, we get time equals distance divided by velocity. 50 meters and a closure rate of 5 meters per second, 10 seconds. So the trains will collide in 10 seconds. Now where? Again, where is the question that was a tough one to answer if you just keep track of where one train is relative to the ground and the other one relative to the ground. Click forward in time, 1 click, 2 click, 3 click, 4 click, and try and find out when they try to occupy the same space at the same time. Well, with this information, by changing our frame of reference to talk about a closure speed or a relative speed, the speed instead of a speed of the train relative to the earth or the track, we speak of the speed of the train relative to the other train, and that got us right to a collision occurring in 10 seconds. Well, but we also know how fast the trains are going, and therefore we know where they'll be in 10 seconds. Now really, I could choose either train. In fact, maybe I should choose both to check my answer. Let's take the leading train. For leading train, the distance is its velocity times time, which it's traveling here at v2 is 15 meters per second for 10 seconds. That's the 10 seconds until the collision, which gives me 150 meters. Now what does that mean? That means 150 meters from its present location. So if this is 50, then we're going to use 50, 50, 50, and we'll say it's here. Okay, so we expect that the collision occurs here. (150 meters from the location of this train. Now notice that that is equivalent to saying 200 meters from the present location of the following train. Why don't we check? check other train. V1. We have d equals vt, and that train is traveling at 20 meters per second. And it's going to travel for 10 seconds until the collision, because we are claiming that they arrive at the same location in space at 10 seconds. This train has traveled 200 meters in the same 10 seconds. What does that mean? That means 200 meters from its present location, which is here, 50 plus 150. Indeed, that is the same location as we previously figured out. Train 2 will be. This was a redundant calculation. We knew it had to come out right, but it was worth a check and worth seeing your first time around.